Output visible?
No, sir. It's black.
It is dark.
Now?
Yes, sir.
Visible.
So how many of you tried yesterday's problem?
Yes, sir. I've tried.
Yes, sir. I've tried.
Who is this? Biplab.
Yes, sir.
And who else?
Sir, Rupam Samant.
Yeah, Rupam. You had sent, right?
Yes, sir. Yes, sir.
Yes, okay. What about others? Okay, anyway, we will do it now again. Okay, so what we were doing was we had chosen this P as del cross A, right? And your E as minus of grad phi minus del A by del T, right? And our intention was to, using this B and E, we want to get the potential. Okay, so what is the potential for a particle moving in an electromagnetic field? So our force, Lorentz force. So we had written this force as Q minus del phi minus del A by del T plus V cross del cross A, right? And then we were trying to get the X component of this electromagnetic force. So we had written, okay, so to get the X component, so we were trying to solve this. Okay, so if I want to get this, so I can write this as X cap, Y cap, Z cap, and then Vx, Vy, Vz. And for time being, I write this as del cross A, X component, del cross A, Y component, del cross A, Z component. Did I start recording?
No, sir.
I'll start it now. Okay. Okay, so I can write this in a matrix form. So if I want only X component, so for X component of the force, what I do, only the X component, this again Q into, you have minus del phi by del X, only the X part of it, del AX by del T, plus the X component of E will be Vy into this minus Vz into this, right? So I can write Vy del cross A, the Z component, minus Vz del cross A, del cross A, the this Y, right? Now you can solve this also. So this is what? X cap, Y cap, Z cap. del x, del y, del z, and then ax, ay, az. So only the z component of this, let me write it here, minus del phi by del x minus del ax by del t plus vy into the z component of it. That means del x of ay, right? Del x of ay minus del y of ax, right? Minus vz into the y component of this. So what is the y component of this? This minus this, right? Del x and minus of that, right? So you have to make the sign arrangement of that, right? So vy del y of ax minus vy del x of ax of del y of ax, right? Minus vz and this minus this with negative sign, right? So I should write here plus del x of az minus del z of x, right? And here itself I write what is my uh, del ax by del t. So if I expand this, so a is a function of x, y, and z. So if I take dA by dt, only the x component of it is del ax by del t plus del ax by del x plus into x dot, right? Into x dot. So that is your vx. So vx plus del del ax component of with y and xy depend on time. So that will give you x. So y dot is nothing but your vy and plus your del ax by del z dot, that is your vz, right? Okay. So from here I can write del ax by del t is minus of dax by dt minus all these quantities, right? So I can write vx del ax by del x minus vy del ax by del So this quantity I write here directly. So dax instead of del ax by del t, I will write dax minus of dax by dt minus all these quantities. So you just check it. This sign minus sign and with this minus sign they will become plus. So what do you have is minus dax by dt, okay, and then plus plus this vx del ax by del t del x plus vy del ay by del ax by del y and then this term plus Vz del Ax by del Z. So this we are writing for this. Okay, here this del Ax by del T is nothing but this. Plus you have all this term Vy del Ay by del X minus Vy del Ax by del Y plus Vz del Az by del X minus Vz del Ax by del Z. Now you can see here these Vy del Ax by del Y and Vy del Ax by del Y. This is plus and this will get cancelled. Vz del Ax by del Z and Vz del Ax by del Z, this will get cancelled. Okay, so you only have the x component of this as q minus del phi by del x minus dAx by dt as it is. Okay, and what remains plus Vx del Ax. So continue on another page. So what you have is fx as q and minus del phi by del x minus dx by dt as it is plus Vx del Ax by del x then plus Vy del Ay by del x plus Vz del Az by del x. Okay, and now you can write this fx q minus del phi by del x dAx by dt plus, now see here, this you can write it as del x of v dot a. Okay, v anyway, if you expand this, if you take this is going to again come back to this. Okay, so if you expand this, okay, so if I take del x of vx ax, okay, this doesn't del x of vx is anyway is going to be 0, so only del x of ax you will have. Okay, so vx, if you apply the product rule, so you will have vx into del ax by del x. Okay, and del x of vx is again going to be 0, so this will give you back this. Okay, and now what about this term? Again I can write it as dAx by dt. Okay, just a simple del. So only the x component I want, so v dot. So can I write it like this? See, what is my v dot ax? V dot a.
Yes, sir.
V dot a is my vx ax plus vy ay plus vz az, and del x del vx of this, so only the first term. Okay, only the first term. So what you have is ax, right? This and ddt of that. So ddt of that. So you are this and this. So both the terms are equal. So we are writing the same thing in a different fashion. Okay. Is this clear to everyone?
Yes, sir.
And now, so the x component f of x is q, right? Minus, please mute your mic. Minus del x of del x of phi. Okay. So I take these two terms together. So phi minus, so minus of minus, this will give you plus b dot a, correct? And minus ddt of, for this, I can use this ddt of del vx of v dot a, right? Now again, phi is a function of x, y, and z, right? So if I take del phi vx of this will make no difference, make no difference in that. So I can this again write it as f of x as the x component of the electromagnetic force as phi minus v dot a minus ddt of phi minus v dot, right?
Then the sign should be plus because we are exchanging the v sign.
Vx sign should be
Plus, sir. Means
yes,
ddt is
this will become plus, correct, right? So del vx of this. So now this you can write it as your potential. Okay, so in final form, this you can write it as minus delta x of u plus ddt of del vx of u. Okay, where your u is phi minus v dot. And you can put q as your one. Okay, so q is there. Okay, so put your q as, right. So is this clear to everyone?
yes, sir.
So there are several ways you can show it. We did a little mistake while doing that yesterday. Okay, so your potential is now this potential is velocity dependent potential. So from here you can write your L. Let me check my list. Right, so your u is now phi minus v dot a. So your L is, L, you write t minus u, and your u is this. So if I write completely, so L is my t minus u. And next, what I showed is your mechanical momentum, right? So you write L as T minus U, and U is now your phi minus V dot A. So if I write in complete form, so this T kinetic energy, you can write it as mq dot square minus phi plus V dot A. This will be your Lagrangian, right? This will be your Lagrangian. And if you want to get the canonical momentum, we have written this P, you write it as del L by del Q dot, right? So your canonical momentum will be from here, this will be mq dot plus Q dot is nothing but your, so this you can write V as your Q dot. V is your Q dot, so you can write it as A. So this is your canonical momentum. So if you check here, this is your normal mechanical momentum, and you have an additional term here, additional. So, so this momentum, I mean, it can be anything. So it need not have the dimension of momentum only. So this canonical momentum is different. So it has mechanical momentum plus additional terms are there. Okay. Unfortunately, we have to use the same notation what we use for our normal momentum. So P is basically, so you basically write P canonical as your mechanical momentum plus this additional term. Okay, so that was there. So you can write Hamiltonian also. Hamiltonian is your H. So from previously we have seen that this Hamiltonian you can write it as summation over P Q dot minus L, right? P Q dot minus L. So you can write this. You can write this Hamiltonian for this electromagnetic system. So particle in a particle moving in an electromagnetic system. So this H again you can write it as P canonical. P canonical is your, okay. Let's write in a different way. So half m q dot square minus phi plus v dot a. This is, let's do it like this. This is your canonical. And you can write Hamiltonian as T plus V, right? So let's write P dot A. So your P and Q dot. So this will give you what? If I write this, so for only one system, P Q dot, right? P Q dot, and your canonical momentum I have written P as Q dot minus your half n Q dot square minus phi plus phi minus V dot. So this will give you Q dot dot square minus mq dot square plus qa dot, this is second, right, q dot plus qa dot this will get cancelled plus 5, and then you have mq dot minus this as your minus 2 minus 1. So this will be half mq dot square plus 5. Okay, so h will be t plus v. Yes.
So the page is
not
not visible.
visible.
It's the previous one page, I think.
So I did everything on this page. Oh shit. Okay. So what I did, I wrote, so pq dot, p, you know this, p is my mq dot a. So I substituted p for p here, this term, and q dot as it is. L is my whole this term, right? So I just substitute that. So if I change h is my summation over pq dot minus L. So L we have just written here. What is happening with this? Half mq dot square minus 5 plus q dot a. So I write here L as my half mq dot square minus 5 plus I write q dot a, and then uh, uh, p is my p is my mq dot plus a, right? So p is my mq dot plus a. So if I substitute these quantities here for L and is, I get h as half mq dot square plus 5 plus 5. So this is your kinetic energy and this is your potential. So you have T plus V as your total energy in your system. Okay. So
But so we have to replace the q dot, right? Because it's Hamiltonian.
what?
So it's Hamiltonian. So
Hamiltonian is?
So I'm saying that it's Hamiltonian, right? So we have to replace the q dot in term of p.
Yes. So that you can do again easily. So in terms of so what I have written, this is in mechanical form. So what is this? So this is your p square by twice m, right? Plus 5, and p square just now you saw p is your p canonical is your mq dot plus a. So this is your mechanical momentum. This mechanical momentum p, I can write p mechanical as p canonical minus a. So I can use this here, p canonical minus a whole square by twice m plus 5. So this is your Hamiltonian. So I just wanted to show that this h, L you write as t minus u, h you write as t plus u. Okay, so this total energy of your system. Is this correct?
Yes, clear.
So I'll
Yes, sir.
So there will be one problem. I'll keep it for tutorial. We will not show it here now. So you can write it down and try it. Okay. Again, it will be there in the tutorial also. So show that if the potential U in the Lagrangian contains velocity dependent term, the canonical momentum corresponding to a coordinate of rotation theta of the entire system is no longer the mechanical angular momentum. Okay, so you can use that notation L theta. Or I can give you, but it is, so L theta canonical is actually L theta your normal minus summation over I n cap dot r cross gradient of. Okay, so that n cap is the unit direction in your angular momentum. Okay, you can see this in your next tutorial. You try this at home. So next we will go in general you can write so. So in complete form, we have written this, right? So let me, what we were doing yesterday was we use this E as minus grade phi, this del A by del T, B as del cross A, and finally actually so we have tried this. We have derived the potential using using these. Okay, and so what we have gotten is your at the end we gotten this Q in total with all X and Y components as LA by del T is Q. So These term actually we were yesterday got confused. So remember that this V dot del, okay, this is not equal to your del dot V. Okay, this term is actually scalar. This is scalar. Okay, so if I write this in separate form, so that will give me Vx into x cap plus Vy into y cap. Small things. So Vx into x cap plus Vy into y cap plus Vz into z cap dotted with your x cap del x plus y cap del y plus z cap plus z cap into del z. Okay, and the right hand side is what? This is some simply, so if you dot this, you will get Vx into del x, right? If I do the dot product of this, you will have Vx into del x plus Vy into del y plus Vz into del z. So you check this. This is an operator, right? So this is an operator, and this portion is actually a scalar. So they are not equal, and that's why yesterday we got confused. Okay, so you can do in this form also. So when we solve this completely, what you can write your f as q gradient of phi minus v dot a minus q del a by del t plus a into v dot del. Okay, a into v dot. Is this visible to everyone? Some issue is coming. I have to. This pen has become very sensitive. Okay, and now you can write this as minus sign is there. Q del phi minus v dot a and minus q, and this del t. So del t plus v dot l operated on. Okay, so this is nothing but your total derivative of the
DDT.
yes. Okay, so you can check again that taking a as your function of x, y, z, and okay. So, and then so this will come into final form as y minus v dot a minus q dA by dt, and dA by dt we have, you can write this a as del del v of phi minus v dot. So same thing what we did before. So in final form you can write this f as minus q del phi minus v dot a plus q into ddt of del del v of phi minus v dot. Okay, so that is what so gradient of, so this is v q ddt of del del v of, okay. So there are several ways you can do it, so specific. So I think Biplab. Yesterday who sent me the solution in
Sir, Rupam.
Rupam, sorry. So Rupam did it in another way. You can follow whichever is convenient for you.
And sir, I have proved the means vector identity using Levi-Civita tensor. So
yes, Levi-Civita tensor, that is also correct. I mean, there is no issue in that. Okay. So our Hamiltonian, we have seen that our Hamiltonian is this H. You can write it as P canonical. H is your P canonical minus A whole square by twice m plus phi. Okay, so your H is basically a function of canonical momentum, your generalized coordinates. Okay, so if I write it in R form, you can write Q also, R and T. And usually your Lagrangian was in the as the for this your so in general you write L as Q dot T, and H you write it as function of P, Q and T. Okay, so here you be careful that this Q and Q dot, they are not functionally independent. What is functionally independent? We will come to this again. Okay, when we'll make the transformations. Okay, so but here P and Q, so they are not functionally independent. These P and Q are functionally independent.
This means there is some constant equation.
Yes, they are related to each other. Q and Q dot. When you make the equation of motion, not equation of motion, when you write these Q and Q dots, here Q dots are dependent on Q. So velocity dependent potential. Q dots are dependent on Q, right? So, but here this canonical momentum and this Q, they are totally independent of each other. So when you sum them, they are independent. Each term in that is independently equal to 0. We'll come to that again. I'll go through that Legendre transformation and Legendre transformation, how these components get independently equal to 0. Okay. So H is a function of canonical momentum, generalized coordinate, and T, and Lagrange's is generalized velocities, generalized velocity, generalized coordinate, and T. Okay, so with this we will try to get Hamilton's equation of motion. So now, as you know, your H is a function of P, Q, and T. If I take the total derivative of this dH, I can write it as del H by del Qj dQj plus del H by del Pj dPj plus del H by del T dt. Okay, and from the previous equation, what we have written, H, or we can write also as summation over Pj Qj dot minus L, where L is a function of Q, Qj dot, and T. So if I take total derivative of this dH, you can write it as Pj dQj dot plus Qj dot Pj minus del L by del Qj dot dQj dot minus del L by del Qj dQj minus del L by del T dt, right? Del L by del T. Del L by del Q J dot del L by del Q J dQj, right? So, and from our Lagrange's equation of motion, you know that or Lagrange, this canonical momentum, you can write del L by del Qj dot, right? This term is nothing but your Pj, right? This term is your nothing but Pj. So if I write Pj dQj dot minus of this and this Pj dQj dot, they get cancelled. So you are left with this, and del L by del Qj dot. Del L by del Qj dot is nothing but your Pj dot. Pj dot. So what you left with is dH as your Qj dot dPj minus Pj dot dQj minus del L by del T dt. So this is your second equation, and the first equation need some solution for this. This is your first equation. What is happening? Del L by del T dt. So this is your one equation, and the other previous equation is your this. Okay. So here P and Q, they are independent. Okay. So since P and Q are independent, the coefficient of each dPj and dQj, they are mutually independent, so their coefficient should match. Okay. So these coefficients should match. These coefficient of dPj and dQj should match with the coefficients of this dqj and dpj. Okay, so if you compare, what you have is, so here P and Q are independent. So the variation dpj and dqj and dt are mutually independent of each other, and therefore their coefficient should match. So what you have, qj dot as your del h by del pj, and pj dot as minus of del h by del qj. Okay, and your del h by del t is minus del l by del t. Okay, here j is varying from 1 to up to. So these are n first order differential equations, right? First order differential equations. This is first order differential equation. This is first order differential equation. So total 2n first order differential equation. And these equations are called basically your Hamilton's equation, okay, or sometimes called canonical equation. So they have so is this clear to everyone?
Yes, sir.
There is nothing much. So you have to just take total time derivative and then equate them. Okay. So only now what we have gotten, I mean, in Lagrangian you have n second order differential equations. Okay, and here in Hamiltonian you have 2n first order differential equations. So most of the time it is very easy to solve. Only problem is you have suppose you have two generalized coordinate, then in Lagrangian you solve two second order differential equation, then you will have, if you solve it by Hamiltonian, then for 2 you will have 4 first order differential equations. Many of the time it is easy to solve. Okay, so and this is done. So what I wanted to tell is, something missing. So after that, I wanted to go through this. Basically, when you go from Lagrangian to Hamiltonian, you are making some transformation. So we are going from this q dot t to Hamiltonian. You are making some kind of transformations. Okay, and these transformations leads to symmetry. So a general proof of this I wanted to give. Okay, and the phase space volume actually is conserved, and how it is there, that I wanted to show. So general proof I will give you, maybe next lecture we will do it. And and then how this Legendre transformations, there is one-to-one correspondence. So with a basic example, with how this Legendre transformation is going on, okay, that we'll see. Okay, so when we are making this transformation, basically it leads to conservation. And as I told in previous lectures also, this conservation leads to some kind of symmetry. So the very general proof of that, the Noether's first theorem, that we will see in the next lecture. So if you have any questions so far, we have done. Any questions? If no questions, try to revise that, and then we'll see. If you have any question, you can ask on WhatsApp also.
Hello, sir.
Yes.
So whenever you have written the last expression for the fx, so we can write it in two forms, right? So we can input the q within the bracket also, and we can define in such a way like u equal to phi minus phi dot a or u equal to q into phi minus phi dot a, right? There are two ways of defining u, the potential function.
Yes, yes. So
yes.
you.
So sir, so sir, the left hand side, it is in general is force, right? But if we define u equal to phi minus phi dot a, then we have to pull that q in the left hand side, so it becomes f by q, right? So then only the generalized force dimension becomes equal to the force direction, not equal to the force dimension. That's in general, we know that the dimensions cannot be equal. Like generalized force dimension can be equal to the dimension of the force in general.
Yes. It is not clear what you are saying.
Sir, actually, here we have used the generalized force expression in the in those systems where potential is dependent on velocity, right?
Yes.
Yes. So, sir, the So in the last expression, we have small q. Small q means the charge, not the coordinate. The charge q.
This.
Yes, sir. Yes, sir. That q.
Huh.
We can take it within a common bracket, and then we can define it as f by q equal to, then
yes.
the u function should be there.
Here q and there will be c factor also.
So sir, there are two possibilities. Like we can define two kind of general means one kind of generalized force is which has the same dimension with force, and another one is which has different dimension with force.
Right.
Okay, sir.
Okay, then we will stop here. Okay.
Okay. Thank you, sir.
Yes.